Excuse me, sir, do you know how fast you were going? According to my calculations, you're exceeding the 15-mile-per-hour speed limit at around 3.14 seconds. And since it was that early on in your journey, I believe you accelerated a lot faster than, and in the end, you achieved a speed that was way too high for this area. As a result, I'm gonna have to give you a ticket for speeding and fine you immediately. No, I don't think I was speeding at 3.14 seconds. Are you sure that was the case? Yes, I am sure. My calculations are rarely incorrect, and I believe that they're right in this time. Okay, so you got pulled over by the police because you're supposedly speeding over the 15-mile-per-hour speed limit at 3.14 seconds after you started driving from the stoplight. Big whoop. Only problem is, your car doesn't have a speedometer to check what speed you were actually going. Instead, you have a distance-o-meter, which tracks how far you've driven after a stop. You might have been speeding, but want to prove the cop wrong and maintain your integrity as a mathematician. What would you do? I think something was wrong with that cop's calculations. Let's take a closer look at what was going on so we can actually solve this problem and prove him wrong. Alright, so let's talk about what we need to know. The officer says that I was speeding from exactly 3.14 seconds after I started from the stop. However, we need to know exactly when I started speeding and how fast I was going while I was speeding. So, let's address some of the basics. First of all, velocity. What is velocity? Velocity is just distance over time. Basically, how long it takes to get from one point to the other would be your velocity or rate of change. We can also visualize rate of change on a graph. Check out this linear graph, for instance. We can take this point, A, and random point, B, and find the rate of change between those 2 points. And the x would be delta x, or change in x, and the difference in vertical position, or delta y, would be our change in our height. This would be our rate of change, or slope, as you'd see in a graph form. This is where you find the delta y over delta x, or rise over run. In this case, we can find any point along this line. Say we find another point C. This one, we could take this smaller one, delta y sub 1 and delta x sub 1, to get our other rate of change to equal this new rise over run. One thing you'll notice, however, these two proportions are exactly the same. This means that this rate of change, delta y over delta x, is exactly the same as delta y prime over delta x prime. Therefore, we can conclude from any point along this line, we will have the same exact slope or rate of change since it's a linear motion. However, this would only work if my car was moving at a constant speed throughout the entire duration. Our case is not the same. Our car was accelerating from stopping at the stoplight and being stopped by the police. As a result, we would need to know the instantaneous rate of change at that given point, knowing that our car wasn't actually moving at the same speed the entire way. Let's take a look at what the graph would look like in our situation. Alright, so here's a general graph of what our situation would look like. Over time, as you can see, we're not going at a constant speed. In the beginning, we're slowly, gradually getting up there, while around 4 to 5 seconds, we're speeding up really quick. And then as we get caught by the police, around 7 seconds, we're slowing down once again, going to a stop. To find the average rate of change between 2 points, let's take 4 seconds and 5 seconds for instance, we can just draw this basic linear line as we've seen in the previous graph, and we can calculate change in y and change in x. As we can see here, this gives us the average rate of change between these 2 points, 4 and 5 seconds. However, if we take another line, let's say from 4 to 3 seconds, we see here this average rate of change is drastically different. The change in x and change in y are on totally different scales, resulting in different rates of change in these 2 time periods. Hence the reason why we cannot use this formula throughout this entire course of time, because it's constantly changing. This is where derivatives come in. Let's take this period of time right here, 3 to 4 seconds, and let's take a closer look at it. Alright, so right here what we have is just a closer look at what's happening between 3 and 4 seconds in time. We see we're going from 8 feet from the start all the way to 16. However, this is not a linear motion, and hence the reason why we're not going at the same speed as is shown in the graph. So if we wanted to find the average velocity, we could easily just get the change in x right here, which is 1 second, and change in y, which would be 8 seconds. Easy enough. but that's for the entire interval. We want to get a little bit closer. Let's say, for instance, we want to get the instantaneous velocity at exactly 3 seconds. So how would we do that? Obviously, the average rate of change in this case would not be applicable, as it is way different from what we're actually trying to find. So let's think about this a little bit differently. If this is the average rate of change for the entire interval, how do we get a more exact velocity for 3 seconds? Well, let's try to make the interval a bit smaller. So instead of going all the way to 4, let's just go halfway. That's your delta x, that's your delta y. And now you have a new rate of change, which is getting a bit closer to what you're trying to find, which is that instantaneous velocity at 3. As we go closer and closer to 3, we can see our delta x is getting smaller and smaller, just as the slope of our line is getting smaller and smaller. So let's take a small number like 0.01, for instance, to use as an example. We can take this random point, let's say it's 0.01 away from 3. This coordinate would be 3.01 and some y coordinate. We can just get the slope between these 2 points by doing 3.01 minus 3, and then just take that y minus 8. As we can see here, this denominator turns into 0.01, that's just our small number in the beginning, and this number correlates with the slope of that line that it makes between the 2 points. Let's give these two values a name. Let's call this numerator dx for change in distance horizontally, and let's just make this d of t, the change in time. The thing you want to notice about dx and delta x is that we're going to be using dx in a different manner. Let's take this number for instance. Right now we're taking dt as 0.01. That's not necessarily the case. As dt gets smaller and smaller, we have a more exact velocity for what's happening at 3 seconds, since this denominator is getting smaller and smaller. We don't want to be exactly 0 because that would just mean that it's having 0 velocity, which is of course not the case. We can then address that dx over dt would be your instantaneous velocity at that moment, where dt is constantly getting smaller and smaller, getting closer to 0. This is where the concept of limits come in, where a value is constantly getting closer and closer to a certain value, but it's never getting there. In our case, it's getting ever so close to 0, but never actually hitting it, because that would make our situation impossible. We can see this visually. As we see in our original change in x and change in y, we have this massive slope, whereas if we get smaller like this, we have a much closer value to what we're aiming for. As we get smaller and smaller, we can see that line is getting ever so close to our actual value at 3. One thing we find interesting about this case is that the value that we do find when we get to the smallest number that we can get to 0 will be the tangent of this point. We call this the tangent line. The slope of this tangent line gives us the exact instantaneous velocity at that given moment. You can think of it as an instantaneous rate of change, as we're just getting the slope at that exact point. Now, if we were to do this method on every single interval on this graph, then we could get any instantaneous speed at any given time. That's what a derivative graph is used for, and that's where we can find out whether or not we were speeding at that moment and at what time were we speeding to prove the cop wrong. Based on the data we have right now, we can do this to gather the exact slope at that point, given the tangent line, and record that data point in our derivative graph to create our new visual that will depict our speed over time. After plotting all these points down, we get a graph that looks a little bit something like this. As you can see, it correlates exactly with the position time graph, where you can see the velocity spikes up when we have really high slopes and rates of change in short time intervals. For instance, from 4 to 6 seconds, we can see the largest spike in velocity due to the fastest acceleration being at those points. Of course, we cannot finalize our answer yet because all our units are still in feet per second. We need to change it into miles per hour since that's what the cop caught us in. Let's do a simple conversion here. Right now, feet over second is our current unit. First, let's change the unit of distance that we're in, feet. Let's change it to miles. To do that, we take the numerator, make that miles, and of course there's 5,280 feet in 1 mile. This proportion is just 1, so we're just multiplying it by 1, which doesn't change the difference. But then we can cancel out these units, leaving us with miles on top. And then since we still have seconds on the bottom, we want to change that into hours. As we know, there are 60 seconds in 1 minute. The seconds cancel out. But now we have minutes in the denominator. We want to get rid of that. Of course, there are 60 minutes in 1 hour. Minutes cancel out. And now we are left with miles per hour in the end. After doing this conversion to each and every value on the derivative graph, we can find out how fast we're going in miles per hour throughout the duration of our car's journey. After doing all those conversions, we can see that the graph, of course, looks the same since there's just the same proportions, just in different units. However, we can clearly see that we were definitely underneath the 15 mile per hour speed limit at 3.14 seconds. However, we were surpassing that limit after 4 seconds, beyond 5 and to 6, but the cop did not catch us for that. And for that reason, we just proved the cop wrong. Let's go check back with what he has to say.
Alright, we're back, and we just proved what he did wrong. What do you have to say for yourself?
Well, I guess you're right. Your math checks out. I guess I was wrong. Gotta go back to class then. Gotta refresh my calculus.
And that, kids, is how you get out of a speeding ticket.
Wait, I thought we were talking about derivatives.
Well, same thing.